All right, so last time we did section 6.3, part 3. Okay, we went through the multi-step transformations, and we discussed the order that we have to make sure we process them in, which is the same order we always use. We went through some examples of the graphs, and then we also did a little bit on the calculator where we figure out how do we set a window that maybe meets certain conditions. Maybe they want you to show 1 cycle or 2 cycles. So we went through how to set the window, and then using the window or the graph in the window as kind of an aid, we can figure out all these things about the graph. I think we even did one where we were able to figure them out without the graph, but the graph can definitely be helpful. So let's take a look at 2 special properties about sine and cosine. These are what we call identities, which means it's a formula that is true all of the time. It's not true for certain values of x, it's true for every value of x. And it basically is explaining that sine and cosine are just phase shifts of each other. So if we graph sine on one axis, or sine on y1, and then put cosine in y2, we can see that the only difference between the 2 graphs is it looks like they've been shifted left or right. And that's all that sine and cosine really are. They're just phase shifts of each other. So let me graph. Actually, let me put this over here. Let's graph sine. And now let's take the cosine and let's shift it pi over 2 radians. How much of a shift is that? How much am I shifting it by, say, in degrees? Nick?
90 degrees.
Yeah, we're doing a 90-degree phase shift, which is a quarter cycle. And we're shifting it a quarter cycle to the, which way is minus going to shift? To the right. Okay, it's going to shift to the right. So I don't think I need an extra set of parentheses around the pi divided by 2 because I want it to do the pi over 2 first, not the minus. The order of operations, I think it should be fine. So there's, no, oh, I know what's wrong. I don't think it's an order of operations thing. What's wrong here? Let's see. How am I, when I typed in those equations, what was I assuming? Yeah?
That you were in radians.
Because that pi over 2 is radians. If I put x minus 90, I think this would work fine. In fact, let's try that first. Let's do x minus 90 and see what happens. X minus 90, hit graph. There's the sine, and there's the cosine, perfect. So the problem was I had it, the calculator was in degrees, but I had typed in an equation in radians. You can't do that. All right. But I can still show you the same property in degrees, that if you take and you shift one of the graphs 90 degrees, you will get the other graph. So what that allows us to do is take a problem that uses, say, sines and turn it into cosines. Or we can take a problem that uses cosines and turn it into sines. Right? So it gives us a way to rewrite equations. That's what that does. And we'll talk more about these identities later on. There's a bunch of identities we're going to study. But there's 2. Any questions on that idea? Sine and cosine are phase shifts of each other. Okay. So the last thing we're going to look at is in this section is solving trig equations. Now there is a way to do this algebraically on a calculator that's not a graphing calculator that is faster. We're going to talk about that, I think, in 6.5. But in 6.3, they just practice solving trig equations on a calculator, and it uses a technique that we've been using all year. So if I wanted to solve this on the graphing calculator, sine of x equals 0.4. Anyone think they could tell me how I would type that in, and then what I would look for once I type that in? Caleb?
We could put y1 as sine of x.
Yep.
And then y2 as equaling 0.4.
Yep.
And then look for the intersection between both.
Yeah. We're going to look for the intersection. Is there anywhere special that we want to focus on when we're looking for the intersection? Nick?
Between 0 and 2 pi.
Right, between 0 and 2 pi, because remember, this is a wave and a horizontal line. If we didn't focus on that section, how many times would the horizontal line cross the wave? Caleb?
Infinitely.
Infinitely many. Well, you either have two options. It's either going to cross infinitely many or not at all. Right? If this is your wave, as long as the horizontal line is within the wave, which for this problem would mean between -1 and 1, you're going to hit that infinitely many times. Now, if they said sine of x equals 1.4, then no, that's not going to work. Okay? Because sine of x doesn't hit 1.4. But in this case, it will hit 0.4, and they want us to focus specifically on where? Between 0 and 2 pi. So by them saying 0 and 2 pi, what units are they assuming they want me to be in? Radians. Yeah, they want us to be in radians. So let's put it in radians. All right, make sure we typed everything in. Looks good. Let's hit graph. And you're basically looking at one full cycle. So we get two different answers. Let's do second calc, intersect, and then we just have to find both. Move your cursor closer to the one on the left, and the first one is actually I'll just put them down here. Okay, so we get 0.41, and the second one we get, second calc intersect, is 2.73. There you go. And those are the two answers. Now, there is a way to do that much faster than having to type something in y1, something in y2, set your window, hit graph, do an intersect, do the guess, do another intersect, do the other guess. I mean, it's not hard, but there's a few things we had to do. Watch how easy I can get this answer just using like a regular scientific calculator, no graphing at all. Okay, what was the problem? Sine of x equals 0.4. 0.389. Wait a minute. I know what I did. You have to actually type in the right thing. And I get 0.4115. If you scroll down, 0.41115, that was one of my answers. Okay, so we're going to talk about what I just did right there in a little bit. But I'm just showing you that graphing is not necessarily the fastest way to do this. Not that hard, but not the fastest. And then that other answer takes a little bit of information you have to know, but the other answer would be pi minus the one that I just had, 2.73007. 2.73007. So there's a reason why I knew to do pi minus the answer I had before. It's not always pi minus, but for this problem it was. And we're going to learn how I knew that at some point. Okay? So there are ways to do this without graphing, but graphing is what we're going to focus on right now. Okay, questions on getting those two intersects? All right. Let's try this one. Let's see. So it says to solve that equation, but my interval, I made a mistake writing it, between 0 and 2 pi. So you generally don't include 0 and 2 pi, because 0 and 2 pi are repeats. If you think of your cycle, that's 0. Well, that's the same point. You're repeating that point at 0. So if you get an answer here, or if you're going to include 0, you don't have to include 2 pi as well. If you do, that's like a repeat. Kind of be like if you think about going from 0 to 360, and you include 0 and you include 360. Well, those are the same thing, so we don't want to include both. All right, so let's try this one the same way. Now, does the graph of cosine, if you don't transform it, normally hit 1.5? No, but we're transforming it. We're doing a vertical stretch by a factor of 2. So by doing that, it will hit 1.5. Right? But if that 2 wasn't there, we would have a horizontal line above the graph, never intersected. So let's type in 2 cosine 0.5x and 1.5. Same window as the last problem. Just make sure it's still set to 0 to 2 pi. And here, let's think about this for a second. We're not even seeing a full cycle. A full cycle would be 2 pi divided by a half. A full cycle of this one would be 4 pi units wide. Our window is only looking at half a cycle. That's okay, that's what they wanted. So we'll do secant, calc, intersect. This time, not really important where you put the cursor because it's going to find the one answer that's already on the screen. Okay, so you get about 1.45. Any questions on that? Yeah?
How do you know what the window they want?
They told me that x was between 0 and 2 pi. So that's how I know my window. There are other answers, like this graph keeps going, like over here, and then you're going to get another answer, but they specifically said they did not want negative answers. They wanted the answer to be greater than 0, greater than or equal. Okay, let's look at this one. Now, some of these you actually can solve algebraically. Not all of them. Okay, so we're not going to worry about, is this a problem you could solve algebraically? We will get to that later on. Let's just graph it and see what happens. Okay, so same approach. Put 3 cosine 0.5x in y1. It's not critical you close the parenthesis. It's fine. And then 2 sine x in y2. 0 to 2 pi again. So window should be all set. Let's hit graph. And this is a little more complicated because we have 2 trig functions crossing. And how many times does it look like they cross each other? 3. I'm not going to do all 3, but if you do secant, calc, intersect, well, the middle one is at pi, and it does look symmetrical. So I'm thinking, if this one is a certain amount of units to the left of pi, the other intersection is probably a certain amount of units to the right. But I'll do one of the intersects. Is there any questions on how you would find that one or that one? Okay, but you do have to find them all. Okay, if it says to find, all answers here, solve means find everything. Okay. All right, and let's take a look at this one. 2 cosine x is greater than negative 1/3. This is an inequality. We're still going to start it out the same way. Put in 2 cosine x. All right, let's do negative 1.3. Same window again, 0 to 2 pi. That's a pretty common window. Hit graph. And this time my answer is not going to be like x equals 1.34. When you do something like that, your answer is a number. What type of thing is my answer going to be here? Yeah?
Like, greater than.
Yep. And what do we call that? When you have, like, you know, a between 2 and 6, if that was my answer. That's an. Yeah? That's an interval. So the answer here is going to be an interval. Now I got to check what they want. Where are we greater than negative 1.3? That's going to happen in 2 sections. In this section and in that section. Okay, should I include or not include the endpoint of that black part on the left? Include. Reason? We have the equal to under it, so we can include that. Should I include or not include that intersection point right there? Not include, right? Because it says that it has to be strictly greater than the red line. So this is going to be an open interval, well, half open. Include or not include the intersection between the red and the black on the right? Not including. How about the endpoint of the one in black? Not including. Because that's strictly a less than, not an equal to. So that's what your interval is basically going to look like. So we're going to have from 0 to something. I need to find what that is. Or from something to 2 pi. I'm able to do the beginning and the end because I know my window. I know the beginning is 0 and I know the end is 2 pi. I need to find both of those intersects. So second calc, intersect. Again, it looks symmetrical, so there's probably symmetry around pi. This one's at 2.27, and the other one is probably the same distance from pi on the other side. But we'll just find it. So that's going to round to 2.28. Calc intersect. Second calc intersect. I do need to move my cursor. And 4.00. And that is how you write the answer. Questions on that? All right, so that finishes up 6.3. That's really everything we study about sine and cosine. Both. Yeah, pretty much graphically. Everything in this section was graphical. Either making a table and sketching or solving equations and inequalities. So you guys have already done the 2 to 23 part. If you're watching this in periods 5, 6, or 7, 8, you guys still need to do the 21 to 23. But in period 1, 2, that will be the first part of the homework. 29 to 32. '36, 39, and 43. And if you are in 5, 6, or 7, 8, you also want to do 21 to 23 with that. All right, so any questions on the assignment? Okay.
Are we periods 2, 3, not 1, 2?
What's that?
Are we periods?
Oh, yeah, you guys are period 2, 3. You're not 1, 2. Thank you. You're 2, 3. All right, so now let's take a look at the time we have left at 6.4. So this will be the last section that we do. Whatever we don't get through today, we'll finish tomorrow. But this section is designed to be done in one full period. So we've got half a period now, so we'll probably get about halfway through it. So in this section, we're going to look at all the other trig functions. So we're not going to spend as much time as we did on sine and cosine. Okay, we're not going to break down the transformations into separate days, because at this point we should, be more comfortable with those. So let's think a little bit about what tangent would look like based on what we know about sine and cosine. So if you remember when we studied unit circle trig, sine was y, cosine was x, and tangent was y over x. Okay, that was section 6.2. So what does that mean tangent could really be rewritten as using this idea right here? Sine is y, cosine is x, but tangent is y over x. So tangent is really, yep.
Sine over cosine.
Yeah, tangent is really sine over cosine. Now, let's think about a few things that might be helpful is when you're trying to make a graph, if you can find where it crosses the x-axis. Well, if something is going to cross the x-axis, that means it has a y value of 0. So I want to think when that would come out to 0. So that's the same as thinking when that would come out to 0. How can a fraction come out to 0? What has to happen? Yeah?
Top number has to be 0.
The top number has to be 0. So the graph of tangent will cross the x-axis or have a value of 0 whenever the numerator is 0. What's the numerator? Sine x. So we should know when sine is 0. Think about your graph of sine. What could you plug in for x and it would make sine 0? Tim?
0, pi, and 2 pi.
Yep, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Basically, every integer multiple of pi is going to cause the graph of tangent to be 0. So it's going to be an x-intercept. All right, now, let's think about that. Can the graph of cosine ever equal 0? I mean, think about just cosine by itself. Does the graph of cosine ever come out to 0?
Yeah.
Basically, I'm asking, does the graph of cosine ever cross the x-axis? Yes, it does. Why would that be a problem here? Yep.
Make it undefined.
Because it would what?
Make it undefined.
It would make it undefined. So we would have a problem. So tangent is going to have undefined values in the graph. What happens when you have an undefined value in your denominator? Well, one of two things. You can get a hole or you can get an asymptote. In this case, we do get an asymptote. And we'll get an asymptote every time the denominator is 0. So if this was at, Tim told us, 0, pi, 2 pi, 3 pi. Let's think about when cosine would be 0. Here's your graph of cosine. What is this value right there? It's the end of the first quarter. What angle? Yep.
Pi over 2.
Pi over 2. How about that value? That's another place where the graph of cosine is 0, and that's going to be a problem for tangent. Michael?
3 pi over 2.
3 pi over 2. The next one would be 1, 3, 5 pi over 2, 7 pi over 2. You're going to have a vertical asymptote in the graph of tangent at every odd multiple of pi over 2. even multiples of pi over 2, well, that's fine. But odd multiples are not fine. So now that we know where it's going to equal 0, and we know where the asymptotes are, let's see if we can draw a tangent. Let's put in some asymptotes. Let's do what we always do. Check a value on each side, and we know the x-intercept. So that should give us a pretty good idea of what this graph is going to look like. So let's put in some asymptotes. Okay, I wrote out some of the asymptotes here again. Pi over 2, 3 pi over 2, the odd multiples of pi over 2. So let's put one in. Let me just do this by hand. So, pi over 2, 3 pi over 2, and that's all I really need. And we know that pi, which is exactly right in the middle, is a root. It's a 0. It's an x-intercept. So the graph is going to go right through there. Now, let's check a point just a little bit to the right of, we'll call that asymptote 1, and let's check a point to the left of asymptote 2 and see what we get. All right, so let's put in tangent. Actually, we don't even really need the table. We could just type this in by hand, but that's fine. So asymptote number 1 is pi over 2. That's kind of a weird number. Usually we have an asymptote at like 3, and then I say, okay, what's a little bigger than 3? And you say 3.001. Well, try pi over 2. You get an error. Can't do that. I want to try a number just a little bigger than pi over 2. So you could type in 1.58, or you could just say, all right, try pi over 2, like this, but then I want to try a value that's a little bigger. So pi over 2 plus 0.001. That's going to just give me a value a little bigger. And then I don't have to think about, well, what's pi over 2? Is it 1.58? I can't remember. The point is, when I go a little bit bigger, I'm way down at negative 1,000. Okay, so way down there. Okay, let's try a value that's a little smaller than 3 pi over 2. So let's put in 3 pi over 2. And I want to be just a little smaller, so minus 0.001. I'm up at positive 1,000. Okay, so way up here. So remember, you have to stay as close to the asymptotes as you can, but you also have to go through that black dot in the middle that's the x-intercept. So what's going to happen? It's going to try to stay very close, but then it has to go through there, but it can't keep going to the right because then it hits, think of that dotted asymptote as like a wall. It hits it and then it's trapped in that section. And that's basically what the graph of tangent looks like. That pattern is repeated over and over by taking what you already drew, make a copy of it, and then just put it in the next section. So the graph of tangent is what we call a discontinuous function. You can't sketch it without lifting your pencil. Right? That's showing 2 cycles of tangent. It's not the best way to show it, though. I think the way I showed it here is better because you're not breaking the cycles up. Here you're showing a half cycle, and a full cycle. All right. It would be better if you're asked to show 2 cycles to maybe set your x min at pi over 2 and set your x max at 5 pi over 2. That would be one way to show 2 cycles. If they don't say which 2 cycles to show, you can show any 2 cycles you want. Right? If I zoom out, there's infinitely many cycles. Pick 2 of them that you want to show. I showed you guys these 2 on the right. All right. So any questions on that? So a couple things we don't really talk about anymore here is amplitude. Amplitude is the distance from the center line of the graph to a maximum. Well, tangent doesn't have a maximum. It goes to infinity. It doesn't have a minimum either. So we won't really talk about amplitude anymore. We can still talk about the period length. And that might be something to kind of look at. What's pi over 2 in degrees?
90.
That's 90. So each one of those red lines is a full cycle of tangent. This cycle starts at 90, and it ends at 3 pi over 2. It's between 90 and 3 pi over 2. What's 3 pi over 2? Yep. 270. What's the difference between those two numbers? Yeah.
180.
180. It's very different than the default cycle for sine and cosine. Sine and cosine have a period length by default of 360. Tangent has a period of 180. That's the normal period for tangent. 180 degrees, or pi. Right? So it naturally cycles a little bit faster than sine or cosine. And we can modify how fast it cycles, just like we can do it with sine and cosine. We could do a horizontal stretch or compression, and it works exactly the same. So we just have to be careful when we talk about the asymptotes here. And if I were to ask you how many asymptotes are in each cycle of sine, or tangent, sorry, tangent. Well, it's kind of like armrests in an auditorium. You can't own both. Right? It's not nice. Right? Now, the person next to you is going to get really mad at you. Right? If everybody agrees to use the, I don't know, unless you're on the end, that's different. But if everybody agrees, okay, I'll use the one on the left, then everybody's happy. Right? Then we don't have a fight over the armrests. So this cycle, we'll call this cycle 1, this is cycle 2. Cycle 1 can't own both of those asymptotes. It doesn't matter how you think of it, but each cycle only owns one asymptote. Okay? Because if we said cycle 1 owned both of them, well, then what would you say for cycle 2? It owns both of them as well? You can't do that because then this asymptote would belong to two of them. Each asymptote only belongs to one cycle. Right? It doesn't matter how you think of it. Say the one on the left. The one on the left belongs to the cycle right after it. Okay? Any questions on that idea? Because if you don't do it that way, then you wouldn't have each cycle with the same number of asymptotes. And an asymptote can't belong to both. All right, so there is one asymptote per period. All right, what else? All right, so cotangent, I'm not going to go through this one in as much detail, but the reasoning to figure out the graph is exactly the same as sine. We know cotangent is the reciprocal of tangent. So now, everywhere that you had a root in the tangent function, what is that going to become in the cotangent? John? An asymptote. Everywhere there was a root, it's going to become an asymptote. How about everywhere where there was an asymptote? What's that going to become? Caleb?
A root.
That's going to become a root. So basically the roots and the asymptotes switch places. So when I show you the graph, bless you, look for an asymptote at pi. Look for one at 2 pi, look for one at 0, and look for roots at pi over 2, 3 pi over 2, and 5 pi over 2. And there we go. So there's a root at pi over 2, and there's an asymptote at 0, and another one at pi. Notice the curvature switches as well. This is a graph that has negative slope versus the graph of tangent is positive slope. It's not a consistent slope because it's a curve, but the graph of cotangent naturally has negative slopes on all the sections. Yes?
How do you put that one into the calculator?
So to graph cotangent, you'd have to type it in. Well, you could type it in like that, cosine over sine, or you could type it in a little bit shorter as 1 over tangent because it's the reciprocal.
Okay, thank you.
Yep. And there's the graph of cotangent. Okay, so tangent and cotangent. Again, same kind of deal with asymptotes. Asymptote can't belong to two cycles. Each asymptote belongs to one cycle, just like in tangent. And let's look at how quickly this graph is cycling. That's one cycle between those two blue lines. This blue line is at 0. This blue line is at 180. The difference between 0 and 180 is 180. Okay, so cotangent has the same period as tangent. It cycles every 180 degrees naturally, without any transformations. Okay, questions on that? All right, so this is basically pointing out what we just said, that the period of tangent and cotangent is pi, or 180. And we had a property we talked about with sine and cosine that said this. Sine equals sine x plus 2 pi, meaning if you add 2 pi to a value, you'll get the same answer as if you don't. Or if you add 4 pi, or if you add 6 pi. All that adding 2 pi does is move you to another cycle, but it still gives you the same answer. An example with a number, sine of 5. Sine of 5 plus 2 pi. Same thing, sine of 5 plus 4 pi. You're getting the exact same answer, just in different cycles. Well, that's what these two properties are saying here about tangent and cotangent. Since tangent and cotangent naturally cycle every pi radians, if you take the tangent of 3, you get that. If you take the tangent of 3 plus pi, you get the same thing. It's just the answer in the next cycle, but it's the same answer as the one before. It doesn't make sense kind of looking at it with the calculator. Think of it like this. I typed in, what did I do? Tangent of 3. Well, the tangent of 3, if you were going to solve it like we did in the last section, it's right there. The tangent of 3 plus pi, it's right there. That's the same answer. The answer is the y value, and you're at exactly the same height as you were in the previous cycle. That's why adding and subtracting pi will always give you the same answer when you're dealing with tangent and cotangent. Again, n here would have to be an integer, because when you add pi, you can add 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. You have to add a whole cycle. If you add like half a cycle, then you're not going to land in the right spot. All right, so transformations. Guess how transformations are going to work? They're going to work exactly the same as they do for everything else we've studied all year. So I'm not going to write it out in as much detail. You could look back at what we did for sine and cosine, to A, B, C, and D, and just change sine to tangent, and there you go. You've got everything. Well, actually, I guess I am going to write it out. So there's your formula we've been writing. A is your horizontal shift. B is your period change. C, again, we don't want to call that an amplitude change. That's more of the vertical stretch. And D is a vertical shift. Yeah, you can really replace that with sine, cosine, tangent, secant, cosecant. You can replace it with any trig function, and all that is true. These could be plus or minus. Just really quick again on a phase shift. plus moves it which way? Left, minus, right, vertical shift, plus would move it minus.
Down.
Yeah. If B or C was a negative, causes, yep, flip or reflection. Yep. All right. So what was our formula to find the period of sine or cosine? It was something over B. What was it for sine and cosine? Yep. It was 2 pi over B. Because 2 pi was the natural cycle length of sine and cosine. Well, what's the natural cycle length for tangent and cotangent? Yep. Pi. So if you want to find the period of tangent or cotangent, you're not going to use 2 pi over b. That's for sine and cosine. It's also for secant and cosecant. So whenever you're doing tangent or cotangent, that is the formula you use to find the period. And one thing that you're going to be asked about is how do you find the asymptotes in the tangent, cotangent, or secant or cosecant function? Well, we know where they are if we don't do anything to the function. We can go back, look at this graph, and I told you that the asymptotes for cotangent occur there, and the asymptotes for tangent occur there. And I tried to point out the pattern. Well, if you do a transformation, those asymptotes are going to change. They're not necessarily going to be in the same spots. So, how do you find the asymptotes in any trig function when you do a transformation? Well, the first thing is you have to know what the asymptotes are in the original. Just like when we sketch a transformation of sine and cosine. We have to know the original points first. So you want to find all the asymptotes in one period of the original function. For tangent and for cotangent, there is only one asymptote in each cycle. For secant and cosecant, that's not true. There are 2 asymptotes per cycle. Okay, when we get to that. That might be tomorrow. But for tangent and cotangent, there is 1 asymptote per cycle. You set the original asymptote or asymptotes. In the case of tangent, it's just asymptote. Set the original asymptote equal to your argument and solve. What that's going to do is tell you where that specific asymptote moved to. But when we look at the graph of tangent, if you zoom out, how many asymptotes are there? Nick?
Infinite.
There's infinitely many. You need to describe them all. And by describing them all, I don't mean to write every single one of them down. That's not how to do it. If I go back to cotangent, the way I would describe all the asymptotes in cotangent in general is I would say the asymptotes are of the form pi n. Or actually, I'd probably say n pi, where n is an integer. 3 pi, 4 pi, 5 pi, 6 pi. So this is a formula that describes all the asymptotes, not just one of them. Okay. N times pi will always give you an asymptote in cotangent, as long as n is an integer. All right, so we find our original asymptote, set it equal to the argument and solve. And then we can describe all of the asymptotes using a formula. Remember that in a trig function, it's periodic. So if you know where one thing is, then you know where the next time it's going to happen is, because it's going to happen one period later. And then when's the next asymptote after that? One period later. What about the next asymptote? 1 period later. Everything always occurs very regularly in trig functions. So this is a specific asymptote that you'll find from step 2. And then you add period times n, and this is basically saying that this asymptote will repeat every single cycle. That's what period times n means. Let's see if I have an example of that. All right, so find the period, and then let's see, come up with a viewing rectangle that shows 3 cycles of the graph. Okay. So, what is the period formula in this case? Nick?
Pi divided by 2.
Pi divided by 2. That's the period. Now, if I want to show 3 cycles, I need a window that's triple the period. So I could try 0 to 3 pi over 2. That would triple the length of pi over 2. All right, so let's try 0 to 3 pi over 2. Everything else is fine. You just have to type in tangent 2x. No, that's okay. That's 3. That is 3 cycles. It's a half, a whole, and a half. So if it said 3 cycles on the test and you gave me that window, I'd give you credit. But if you want to show 3 cycles not broken up, you'd have to adjust your window a little bit. You'd have to slide everything maybe to the right or to the left. But again, that would be okay. So we'll just go with that. All right. Now let's just finish up by describing the asymptotes. If you don't remember what the asymptotes are, I'm going to give you a chart tomorrow that is a summary of all the asymptotes. But I'm going to wait until we study secant and cosecant. So the first asymptote you come across in the tangent function is at pi over 2. That's the first positive one. To find the new asymptotes, we set that equal to the argument, solve it, and then put the plus the period times n. Now we've already got the period. Nick told us that. So this part's done. What we need to figure out is when I get there we go. We need that. This is the location of that asymptote after you do the transformation to it. So, how do we find out where the original asymptote moved to? Set the original asymptote equal to the argument and solve. So, that's the original asymptote that we always use for tangent. What's the argument in this case?
2.
2x. It's this whole thing. Right? So set that equal to 2x. And how would you solve that? Yeah.
I mean, the 2's just cross out, so you're just left with times x. Never mind. That was really dumb of me.
Yeah, the 2's don't cancel. This was
Yeah.
multiplication, they would cancel.
Yeah, you divide each side by 2.
Divide each side by 2, which basically means times a half. That's all right. And what's half of pi over 2? John?
Pi over 4.
Pi over 4. So, I already wrote asymptotes. I don't know where it went. So this asymptote is going to move to pi over 4 after you do that transformation. The horizontal compression by a factor of 2. So that asymptote is now at pi over 4, and you have to tell me how often that asymptote is going to repeat. How do you explain that? You tell me that it's going to repeat every cycle. So you put plus the period times n. Those are all the vertical asymptotes in this problem. The first one is at pi over 4, and that one will repeat forever, every pi over 2 radians. Left and right. We'll talk more about describing asymptotes tomorrow. We're actually almost done the section. We just have to talk about secant and cosecant. All right, so for the homework, we've got those few questions I put up earlier in the video. And let me adjust this, because I have to take out all the secant and cosecant problems. Skip that one. 3 is okay. 6. We'll skip that one for now. Let's do 7. We'll skip 8. Skip 9. Put that in 12. 13. That's okay. 15. We'll skip that. 20. That's okay. 28. We'll skip that one for now. 29, 30. Get rid of that. 34. That's fine. And 45, 46, 47, and we'll skip 48. All right, I'll just erase. So what's written on the board, that's the homework. So 3, 7, 12, 13, 20, 29, 30, 34, 45, 46, 47. Okay, and the other 6 or so questions from the other page. I'll copy and paste them here, make it look nice and neat so you can find it at the end of the video. Okay, so that's the full homework for tonight, the problems that were from earlier in the video, and the ones that we just did on tangent and cotangent.